Hello dear students, I am happy to record this video for you again. We are in the continuation of the linear algebras part or subject. In this subject, after sixth section about the system and how to solve the linear equation with the system and using the matrix, inverse matrix, determinant of matrix and Cramer's rule. Now we have new subjects here. We have eigenvalue and eigenvectors. So we have eigenvalues and eigenvectors together. Eigenvalue and eigenvectors are very important in the engineering departments or any other department because most of the problem depends on the eigenvalue and eigenvectors. The first of all, this preparation, this example really is a preparation for you in the page 136 for understanding what's the meaning of the eigenvalue and eigenvector. Eigenvalue is such value like a lambda. We recall as a lambda. In general, internationally, they recalled as a lambda. Each lambda has got multiply any things. For example, we say we have a vector A, a big vector, and a small vector like a U. We recall U as eigenvectors. So for finding the eigenvalue is what? Our vector multiply U. If you can find the common number, do not forget number, factor or number, any number, and you get the U itself, so means that we have what? This number is eigenvalue. For more understanding, the question that asks you in the first example, you say just to prepare, as I told you, to prepare the subject, we have A is equal to 1, 1, minus 2, 4, and U is equal to 1, 1. So find or show that, find the lambda. Or this is the first type of the question. Or maybe say, show that lambda is equal to 2 is eigenvalue to this problem. So first of all, I say A U multiply U is equal to 1, 1 minus 2, 4 multiply U 1, 1. We say is equal to what? After multiplying, you can see is equal to 2, 2. And you can see there's a common between here. You can say U is equal to 1, 1. So here's a U is equal to lambda U. Lambda is equal to, this is a vector, this is a number, our vector, and this is the number which we recalled eigenvalue. That's also, yes, eigenvalue is equal to 2, or you can say yes, that 2 is our eigenvalues. The same is true for the part B of this example. You can find the eigenvalue here was equal to 3. Okay, dear, because AV, here's A, here's V, is equal to some number to V. So here's lambda. That's all. How about this is easy for 2, matrix 2 by 2. How about the 3 by 3? The same. Nothing changed. We have A and we have U. We multiply AU. I guess such a result. It should be U, and here's the number. The number will be our what? The number will be our eigenvalue. So eigenvalue is what? Is 2. And do not forget about these concepts. When I mean concepts, I mean eigenvalue and eigenvector. The number, we have A, this is a matrix. U will be our eigenvector. Okay? And the lambda will be what? Eigenvalue. Do not forget about these concepts. That's all about the first page in your lecture note. Now we are going to we are going to talk about the characteristic equation. The characteristic equation is what? Is to find, what we use the characteristic is to find the eigenvalue. So in that case, maybe we will make an example as we say AU is equal to lambda U, and we can bring this one, and you know, between number and such vectors, we can say is minus lambda U is equal to 0. We bring it to the left side. And you know, if I take a U as a common, it remains what? Lambda. We will multiply by I because we need matrix should be the difference with the other matrix. That's why we put I here is equal to 0. This is our important equation, which we called characteristic equation for eigenvalue. And be sure that if these all a u is equal to 0, means that has infinite. Okay, if this like a system, if we have equal to 0, we say the system or this equation has infinite solution, as we did before in the system, if you remember. So this is very important for you, means that the determinant Ax has an infinite number of solutions if and only if determinant of A is equal to 0. So it means that if you have a matrix A, we say this A is our matrix. If we have A is any matrix, if A determinant of A equal to 0, so it means that the characteristic equation A minus lambda IU has infinite solution, which is not good for us because we need really the exact solution. So that's why we are going to find the determinant of here to be 0, which is very important because to find the eigenvalue is called the characteristic equation. We say that we need to make it as to be equal to 0. So in that case, we are trying to find the eigenvalue, solve this equation to lambda. Then later we put the value of lambda in the system. Then later we find the eigenvalues example. Instead of these old theoretical things, directly we are going to use to find the example 4 in your section, which is in the page 138. I'm going to solve this one for you. A is equal to, it's easy, 0, 1, 3. And he say what? He say find the determine the eigenvalues and eigenvectors. So eigenvalue, maybe each eigenvalue give me more eigenvectors. Maybe eigenvalue give me v1, u1, u2, on u3. I don't know, depends. Or maybe you just give us u1, or maybe give us more than u1. So I am going to show you all these theoretical things together. Here we have what? We have A. To find the eigenvalues, first of all, finding lambda is equal to eigenvalues. You need to solve determinant. Some books write like that. Okay, some book will write that, or maybe they write determinant of A minus lambda I. You know, both of them, they are the same. So we are going to use this one, and in your book you have another to use that one. So first of all, we should use that one. So how we solve this one? Determinant of A is equal to 2, 0, 1, 3 minus lambda 1, 0, 0, 1, as you know, identity, which is equal to 2, 0, 1, 3 minus lambda 0, 0, lambda, okay, which is equal to 2 minus lambda, 0 minus 0, 1 minus 0, 3 minus lambda. In general, the lambda will go to subtract the lambda to the diagonal because we have identity matrix here, that's why. And the determinant of here is equal to what? We know is equal to 2 minus lambda, 3 minus lambda, diagonal, minus of 1 multiplied by 0. So determinant of A minus lambda I is equal to 2 minus lambda, 3 minus lambda. And as you know, we say to find the solution, we have an infinite exact which solution, we should say that A minus lambda I equal to 0, which means that 2 minus lambda, 3 minus lambda equal to 0. Here we go. So we say that 2 minus lambda equal to 0 or 3 minus lambda equal to 0. So lambda 1 is equal to 2 or lambda 2 is equal to 3. Okay, dear? Why we call lambda 1 lambda 2? Because lambda 1 and lambda 2 means we have two eigenvalue, and each eigenvalue corresponding with two, or means that they related to eigenvectors and eigenvectors. That's why. So instead of mixing those together, we are recalled as lambda 1 and lambda 2. Now, this is the first step. Okay, first step. How about the second step? The second step, finding eigenvectors, okay, corresponding or relating to lambda 1. Okay, dear? Okay, so how we find this one? As you know, we say we should use I minus lambda I multiply u. We should find the u. Our work is what? Is to find the u. So how we find the u? And this u is what? The 0. This 0 is 0 vectors. 0 vector. The 0 is not 0 of scalar number like a 0 that we saw before. If the multiplication of here is equal to, for example, 2 by 2, this 0 will be like that. If the multiplication of here, here's the 0. If the multiplication of here is equal to a 3 by 3 matrix, so our 0 will be like that. So that's why we say 0 vector. Okay. So let's go find this value. So we have a, which was 2, 0, 1, 3, okay, minus, as you know, as usual, 2, because our lambda 1 is equal to 2. So we see 2, 2, 0, 0, multiplying u, which is equal to 0 vector. Now we have 2 minus 2 is equal to 0, as you know, and 0 minus 0, 0, 1 minus 1, 3 minus 1, u, multiply u should be what? Because you have 2 by 2, so here should be 2 by something, okay, 2 by 1. Why? Because we know this 2 by 2 means that we are in the R2, and we have two value, that's why we have two values here. So we have in your book rename it as x and y. Maybe I'm going to rename it as a, how do you say, u1, u2, up to you. And how about the 0? The 0 means that we have what? We have u vector. Maybe 0 is equal to 0, 0, or 0 equal to 0, 0, 0. Also, all they are, how do you say, possibility. So in that case, we have just 0, 0, because this is my unknown vectors, u. So if we multiply here, you know how to solve this one, because this is the system, means that 0x sorry, plus 0y is equal to 0, and 1x 1y is equal to 0. And let me give you a note here. Note: eigenvectors shouldn't be 0. You cannot imagine that u is equal to 0. Okay, u shouldn't be 0. Now we are continuing our work. So we have what? We have x plus y, as you see before. In here, x plus y is equal to 0, which means that x is equal to minus y. X is equal to what? X is equal to minus y. In that case, means that how many solution we have? Infinite solution. Why? Maybe x is equal to 1. So in that case, y will be minus 1. Maybe x is equal to 3. Y is equal to minus 3, or any number. So the vectors that I'm imagining is maybe like that, maybe like that, or maybe even x is equal to minus 2. I'll get what? y is equal to 2. So maybe like that. And there's an infinite shape, an infinite possibility for u being as a vector. So that's why I'm going in general. I say u is equal to, if x is equal to s, then y will be minus s. S what? S any number from the real number. So in that case, u will be s and minus s. That's all. The general form of the vectors. So, and you can say u is equal to s, right? 1 and minus 1. So if s 2 square root of 2 minus 2, this is a general form for eigenvectors. That's all. So I got how many eigenvectors? You can get a lot of. For which eigenvalue? For eigenvalue which is equal to 2. Now I'm going to use or to find the second eigenvalue for you with lambda 2 equal to, I forget really about the value of lambda 2. Let me see here. Lambda 2 is equal to 3. So how we find this one? The same method we are going to find it. So you say a minus lambda I u equal to 0. So in that case we have 2013 minus 3003 u equal to 0. It's equal to minus 1 0 1 0. Am I right? U is equal to 0, and we know because you have 2 by 2 is 2 by 1, so I will get what? I will get minus 1 0 1 0 again xy 0 0. Okay dear, so the same thing, we are going to try the same strategy for finding the x and y. When you multiply this one, you say minus x, okay, minus x plus 0y is equal to 0. 1y, 1x plus 0y again is equal to 0. This is equation number 1. Equation number 2. Careful. Minus x is equal to 0. X is equal to 0. Do not say x is equal to 0. Why? Because I gave you a caution. I say that if y is equal to 0, x shouldn't be 0, because u shouldn't be 0 and 0. That's why. Because in that case is that we have the solution. But we need to find the solution. That's why I say what? I say let x be 0, okay, but y not be 0. Or x be not 0, y be 0. One of them. You cannot say both of them. So as he did it in your book, he say x not be 0, let be a value of x. So the vector of y will be like that. That's all. Okay, dear? That's all. So if you take out the s as a common, you can say is equal to s 0 1. That's the general form of eigenvectors of lambda 2 is equal to 3. That's all about the quotient. So careful how to deal with the eigenvalue and eigenvectors. Here you can find the application. You can see the application of eigenvalue, which give you the extension. And here's another example. Please try to do it by yourself. Just the same strategy that we did it before for the example 4, but here in the 140 we have 3 by 3. That's all. So the identity should be like that, and you get it here. You know how to find the determinant of this one, and the value, as you said, you get the 0. Let me find the eigenvalue that he mentioned for you. Here's the eigendeterminant of here, and you are going to use the 0. You know this, we will try to use to the middle row. Why? Because as in 1.6 I told you, this is the strategy for finding the quickly determinant. So that's why you get this determinant. Now, how many eigenvalue? We have 3, right? Lambda is equal to 4, lambda equal to -5, lambda equal to 3. That's all. So each eigenvalue, maybe in the question I say just find the eigenvalue, so it means that you're done. If I ask you to find eigenvector for one of them, eigenvectors for one of the eigenvalues, you can see find the eigenvalue 3. So the same strategy that we did it in the example 4. We have this equation. We are going to find this one. Now u is what? U is 0, 0, 0. How about the 0 is equal to what? 0, 0. Sorry, x, y, z shouldn't be 0, 0. And 0 vector will be 0, 0, 0. That's all. So in here you have x, y, z. You can see they mention everything here. It's clear. And after multiplying, you get that equation, and you know how to solve this system. By any methods, you can use the Cramer rule, any methods, and you can find y is equal to 0, and you can find this here, y is equal to 0, and from here you can say minus 2x plus 4z is equal to 0, and here again you have 3x minus 6z is equal to 0, because from the second we get y 0. And you know how to solve this example together, the equation. The result will be x is equal to what? To z. So it means that we have what? We have x 0 to x, or s 0 to s. That's all. And you know how to find the s as a common. So I'll get 0 to. That's all that we need. Okay, dear. I think it's easy, and here's the summary of the chapter, or the section, sorry, and here's your exercise. Please try to solve these all together. I hope you understand how to find the eigenvalue and eigenvectors. It's very important, because really this subject is one of the most important subjects in mathematics. So please try to do your best and study on that subject. Have a nice time. And this chapter finished. Thank you for listening and being with me for a long time, and I hope all your success in this subject. Bye for now.